Light. It's a simple word, yet it encompasses so much of our existence. From the moment we wake up to the time we go to bed, light is an integral part of our daily lives. It's something we often take for granted. We walk in the sunlight, work under artificial lights, and enjoy the glow of a campfire without a second thought. Yet without it, our world would be a very different place. Imagine a world plunged into perpetual darkness, where the sun never rises and the stars never shine. We need light to see. It illuminates our surroundings, allowing us to navigate and understand the world around us. We need light to grow food. Plants rely on sunlight to perform photosynthesis, a process that converts light energy into chemical energy, sustaining life on Earth. We even need light to tell us about the universe beyond our planet. Through the study of light, astronomers can unravel the mysteries of distant stars and galaxies. Light is a form of energy that travels in waves. These waves are part of the electromagnetic spectrum, which includes everything from radio waves to gamma rays. These waves move incredibly fast. In fact, light is the fastest thing in the universe. In the vacuum of space, light travels at a staggering 186,282 miles per second. This speed is so immense that it can traverse the vast distances of space in a relatively short time. That's fast enough to circle the Earth over 7 times in a single second. This incredible speed allows light from the sun to reach us in just over 8 minutes. But light is more than just speed. It interacts with matter in fascinating ways, reflecting, refracting, and scattering to create the beautiful phenomena we observe. It carries information about the objects it touches. The color, intensity, and direction of light can tell us a lot about the material properties and surface characteristics of those objects. By studying the light from distant stars, we can learn about their temperature, composition, and even their motion. This information helps us understand the life cycles of stars and the dynamics of galaxies. Understanding light means understanding a fundamental aspect of our universe. It is through light that we gain insights into the very fabric of space and time. From the smallest atom to the largest galaxy, light plays a crucial role. It influences the behavior of particles at the quantum level and shapes the structure of the cosmos. Let's dive deeper into the fascinating world of light and its many wonders. Join us as we explore how light impacts our lives, drives scientific discovery, and reveals the secrets of the universe. Imagine a beam of light trapped inside a glass tube, bouncing back and forth. This isn't science fiction, it's a fascinating phenomenon that plays a crucial role in many modern technologies and natural occurrences. This is the magic of total internal reflection, a principle that governs how light behaves under certain conditions. Total internal reflection is the principle that makes fiber optic cables and even desert mirages possible. Fiber optic cables, which are essential for high-speed internet and telecommunications, rely on this principle to function. Similarly, the shimmering mirages seen in deserts are also a result of this fascinating optical phenomenon. When light passes from a denser medium, like water or glass, to a less dense medium, like air, it bends away from the normal. This bending of light is known as refraction. The amount of bending depends on the angle at which the light hits the surface and the difference in density between the two media. The normal is an imaginary line perpendicular to the surface where the light passes. Understanding the normal is key to grasping how light behaves when it transitions between different media. It serves as a reference point for measuring the angles of incidence and refraction. As the angle of incidence increases, the angle of refraction also increases. This means that the light bends more sharply as it enters the less dense medium. However, there is a limit to how much the light can bend. At a certain critical angle, something amazing happens. The light no longer passes into the less dense medium. Instead, it skims along the boundary between the two media. This critical angle is unique to each pair of media and is a fundamental concept in the study of optics. The light is refracted so much that it runs parallel to the surface. This phenomenon is a precursor to total internal reflection. It demonstrates the extreme bending of light at the critical angle, setting the stage for what happens next. Increase the angle even further, and the light is completely reflected back into the denser medium. This is total internal reflection. The light doesn't escape into the less dense medium, but is instead trapped, bouncing back and forth within the denser medium. This is total internal reflection. It's a powerful principle that has numerous applications in both technology and nature. By understanding how light can be trapped and guided, we can harness this phenomenon for various practical uses. This trapped light has revolutionized communication. Fiber optic cables, which use total internal reflection, have transformed how we transmit information. These cables can carry vast amounts of data over long distances with minimal loss, making them indispensable in our digital age. Fiber optic cables use this principle to transmit data as light pulses over vast distances. The light pulses travel through the cables, reflecting off the internal surfaces and maintaining their strength and speed. This allows for incredibly fast and reliable data transmission. These cables, thinner than a human hair, carry information at incredible speeds, forming the backbone of our internet and telecommunications networks. Without total internal reflection, the high-speed internet and global communication systems we rely on today would not be possible. This principle not only connects us, but also drives innovation and progress in countless fields. Mirrors. They reflect our images back to us, but they can do so much more. Concave and convex mirrors, with their curved surfaces, bend light in fascinating ways, creating a range of effects used in everyday objects and scientific instruments. Concave mirrors are curved inward, like the inside of a spoon. They converge light rays, bringing them together at a focal point. This convergence makes objects appear larger when reflected in a concave mirror. Think of a makeup mirror magnifying your features. Convex mirrors, on the other hand, bulge outwards. They diverge light rays, spreading them apart. This divergence makes objects appear smaller, but gives a wider field of view. This is why convex mirrors are often used as security mirrors in stores or as passenger side mirrors in cars. They allow us to see a larger area than a flat mirror would. Section 4. Through the looking glass. Convex and concave lenses. Just as mirrors manipulate light through reflection, lenses do so through refraction. Convex and concave lenses, with their curved surfaces, bend light in specific ways, leading to a range of applications in eyeglasses, cameras, and telescopes. Convex lenses, thicker in the middle than at the edges, converge light rays. They bring parallel light rays to a focal point, creating a magnified and upright image when the object is closer to the lens than the focal point. This property makes convex lenses crucial in magnifying glasses and for correcting far-sightedness. Concave lenses, thinner in the middle and thicker at the edges, diverge light rays. They spread out parallel light rays, making objects appear smaller and further away. Concave lenses are used in eyeglasses to correct nearsightedness. Section 5. Light at Work. Microscopes and Telescopes. In this section, we delve into the fascinating world of optical instruments that have transformed science and our understanding of the universe. The power of lenses is amplified when they work together. By combining multiple lenses, we can achieve magnifications that are impossible with a single lens alone. Microscopes and telescopes, instruments that have revolutionized our understanding of the microscopic world and the vast universe, rely on the precise arrangement of lenses to extend our vision beyond its natural limits. These tools have allowed scientists to explore realms that were once thought to be beyond human reach. Microscopes use a combination of convex lenses to magnify tiny objects. The intricate design of these lenses ensures that even the smallest details are brought into sharp focus. The objective lens, positioned close to the specimen, creates a magnified real image. This image is the first step in the magnification process, capturing the fine details of the specimen. The eyepiece lens then magnifies this image further, allowing us to observe details invisible to the naked eye. This two-step magnification process is what makes microscopes so powerful. From the intricate structures of cells to the delicate wings of insects, microscopes have opened up a world of discovery. Scientists can now study the building blocks of life and the complex structures of tiny organisms in unprecedented detail. Telescopes, on the other hand, allow us to peer deep into space. By collecting and focusing light from distant celestial objects, telescopes reveal the wonders of the universe. Refracting telescopes use a combination of convex lenses to gather and focus light from distant stars and galaxies. This design allows astronomers to observe objects that are light years away with remarkable clarity. The objective lens, with a large diameter to capture more light, creates a real image of the distant object. This large lens is crucial for gathering enough light to see faint and distant objects in the night sky. This image is then magnified by the eyepiece lens, allowing us to observe celestial wonders millions of light-years away. Through the eyepiece, we can see planets, stars, and galaxies in stunning detail, bringing the vastness of space into our view. Both microscopes and telescopes require careful adjustment and calibration to function correctly. Scientists and astronomers spend a significant amount of time ensuring that these instruments are perfectly aligned to provide the best possible images. The development of microscopes and telescopes has a rich history, from the early rudimentary designs to the sophisticated high-tech versions we use today. Each advancement has brought us closer to understanding the world around us and the universe beyond. These instruments have been at the forefront of many scientific discoveries. Microscopes have led to breakthroughs in biology and medicine, while telescopes have expanded our knowledge of astronomy and cosmology. Whether peering into the microscopic world or gazing at the stars, the human eye, aided by these incredible instruments, continues to explore and discover. The journey of discovery is ongoing, with each new observation bringing us closer to understanding the mysteries of life and the universe.